So today we will be covering the final topics in polynomials. These ones I've left for last because they are sort of advanced, and depending on your school you may not even cover some of these topics because they are so out there. In this lecture I'm also going to be going over some very difficult thinking problems, so expect a great deal of math to be written on the board. We're in particular going to go through two different problems, one concept, and if we have time at the end, I will mention something that I said I would skim over in the last lecture, which is the topic of complex roots in polynomials. Okay. Alright, so let's begin first by remembering what a line looks like in a t-chart. This is all the way back from grade 9, except now we are armed with a little bit more knowledge, so I don't know, let's just consider a simple line like 3x plus 2, okay? And let's start with some simple points, -1, 0, 1, 2. And of course you could fill this out. If I put a -2 in there, what do I get? Let's see, -6 plus 2 is -4. And the thing is, I don't even have to plug in these next few numbers. All I know is that a line has this property that for every one step I move to the right, it will move 3 steps up. That's what the slope means. So without even looking at it, I can fill in this, 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 and that just by adding 3 each time. And this, you may recall, is called a first difference. Okay? Now, I want to look at a more difficult example. Of course, that is a quadratic. Let's tackle a simple quadratic like 2x squared plus 1, okay? And see what happens when we try the exact same procedure. So we are going to put -2, -1, 0, 1, and 2. Of course, you can check that this function is even, so whatever numbers I put here will just be mirrored over here. Okay, if you don't believe me, you can try it out for yourself. So if I put in the numbers, right, what do I get? This is 8 plus 1 is 9, 2, 3, 0, 1. Okay, then we have 3 and 9, and that is, yeah, those are our terms. Okay. All right. So obviously we don't get the same nice pattern we had over here. Okay, but is there something that we can deduce from it? Let's try. Let's try and do this. We will put a first difference of 6 here. This is 2, this is 2, this is 6. Maybe we should take care of the signs, whether it's increasing or decreasing. See how here we went +3, +3, +3. Well, here we actually went -6, and then we went -2, and then we went +2, and then we went +6. Something jumps out at me. And the thing that jumps out at me is that these all have the same difference between them. It's 4, right? So from -6 to -2, I add 4. And then here I add 4 as well. And here I add 4 as well. Okay, so we did get something like here, except it wasn't in the first difference, it was in the second difference. And someone clever who may have been just playing around with these may have figured out a pattern, and the pattern has to do with the degree of the polynomial. For linear terms, the first differences are constant. For quadratic or degree 2 polynomials, the second differences are constant. So it would make sense then, and you can actually prove this, although we are not going to do it today because the machinery required to do that is a little more complicated than what we have so far in this course. We can actually prove this fact. And it's an amazing fact that will help us to do some of these really difficult polynomial questions. The fact is that for degree n polynomials, the nth finite difference, the nth difference, I don't know why I put finite in there, the nth difference is constant. I.e., for linear, the first difference is constant. For quadratics, we have the second difference constant. And for cubics, we have the third difference constant. Actually, and so on. Okay? This is a fact that will literally allow you to graph polynomials knowing nothing but a point and a few other little details. Okay? I'm going to present an example that will literally just use points. Okay? So here we go. Now this one's a very difficult question. I'm not gonna lie, this is like quite difficult. On my tests, these types of questions were some of the harder ones. On other tests that I've received and looked at, these types of questions were not here at all. This is why I'm staying on the safe side and teaching it to you anyways, because I don't want you to run into these types of problems in the school term. At the same time, this is a really good review of how to solve these linear equations, even when you have multiple terms floating around. Okay, so here's the question. Suppose f of x passes through, and by the way, f is a polynomial. We're in the polynomial unit, so all of our functions so far are polynomials. So suppose f of x passes through the following points, okay? It goes like this. -2, 11, -1, 8, 0, 3, 1, 2, 2, 11, 3, 36. Now, this thing that I'm holding right here is my test. Okay, a lot of your test questions will be coming from this. This thing here it's tough. Okay, okay, so all you know is that there's a bunch of points, and the only other information that I've told you is that the nth, for a degree n polynomial, the nth differences are the same. So it would make sense that given something as abstract as this, we should try and figure out what differences are the same to at least get an idea of what degree polynomial we're working with here, okay? And hopefully it's not something ridiculous like 6. Alright, let's try. So we're going to make a table just to document everything very carefully. So we have -2, 11. I'm just copying down the points here so that we can check the finite differences. Sorry, we can check the differences. I don't know why I keep saying finite. It reminds me of some other math term. Okay. So we take our first differences. This is a -3. This is a -5. This is a -1. This is a that's a +9. Okay, so this is definitely not linear. I mean, if it wasn't obvious just from looking at the points, it's definitely not linear now. So here we go down by 3, 5. Okay, here we go up by, oh my mental math, +25. Yeah, that sounds about right. Okay, yeah, this is definitely not linear, and I don't think it's going to be quadratic because, let me try. Well, let's do it in a different color actually, just to keep track. So this is our first differences. Then let's do our second differences. So here we have a -2, then we have a +4, then we have a, what is that, +8? No, it's a +10. And then we have a, okay, 9 to 25, that's what, +14 I'm gonna say? +14. And pretty sure I messed something up here. -2, +4, +10, it's 16. I literally can't add. Okay, +16. Alright, not really looking too good. Aha, look at this. Look at this. So, remember, these are your second differences. And here are your third differences. Yes, we have to do this. Here we +6, +6, and +6. So these are constant. So that means our polynomial is cubic. Aha! Okay, so this implies f of x is cubic. Therefore, we can write it as ax cubed plus bx squared plus cx plus d. All of this information doesn't really help us out that much, because we need to figure out what a, b, c, and d are, right? This is just saying, you know, you have a cubic. It doesn't tell you what a, b, c, or d are. Except for one really neat thing, is that we do have a very important point here. We have the point 0,3. Think about what the point 0,3 means. It means that if I plug in a 0 into my polynomial, I get out a 3. And I know my polynomial has to look something like this. If I plug a 0 in here, what's it going to look like? It's just going to be a times 0 plus b times 0 plus c times 0 plus d, and somehow that equals 3. Okay, but these all disappear because they're multiplication by 0, so that means d is equal to 3. Okay, so we got one thing out of that. We got one thing, and that is that this d term here is 3. Now, I want you to pause for a second and think about how you would go about finding a, b, or c. It's not easy. It really isn't. And I'm not going to pretend that it is. However, using some more points here, you can actually figure it out. Okay? So what I want you to do is try and plug in 1 and -1, and just that will give you some sorts of equations in terms of a, b, and c. And we have a theorem in algebra that tells us that if we have 3 unknowns, we need at least 3 equations. So that means we're going to have to pull out an extra point here. Okay? So really, at the end of the day, it's up to you. I believe on my test, I used 1, -1, and 2. Right? So I want you to go ahead and plug in -1, 1, and 2 into this expression that we have for f, and see what equations that yields. I'm going to do it on the side here, but I want you to try and do it on your own. Pause the video. Okay. So for -1, what do we have? We have -a, so f of -1 equals -a plus b minus c plus 3, and we have that it's equal to 8. Then we can try 1, so f of 1, and that's a plus b plus c plus 3 equals 2. Okay? Then if we try f of 2, let me do it in another color. F of 2, what do we get? We get, okay, that's an 8, so 8a, that's 4b, and if I plug in a 2, that gives me 2c plus 3 equals what? 11. Okay? I can do some quick rearranging here just to get rid of the constant terms. So let's go ahead and do that. I'll just move the 3 over to the other side to get me 5. This, of course, becomes -1. And this here becomes 8. Okay? Now maybe you can see out of all these equations there's something nice that you can do. You can factor out a 2 from both sides and divide it out. So this becomes 4a 2b c. 4a 2b c is equal to 4. Alright? Now, in order to make time for everything else that I wanted to get through in this lecture, I'm going to simply show you how to get one of these numbers, one of these variables, and then leave it up to you to figure out the other two. And I really want you to figure out the other two because I guarantee you that I will be able to ask something like this on the test, which is I don't know when the test is. It's like sometime. Okay, so anyways, you will be able to do something with this. I'm going to show you, for example, how to get, let's see, what can I do here? I think I can try maybe getting B. Yeah. And then I'll leave it for you to figure out the other two. Alright, so first thing I'm going to do, just to keep track and organize my work, I'm going to label my equations with the correct colors. I'll try to keep consistency with the colors, but I may end up halfway through getting bored and just writing it all with the same color because switching pens is no easy task. Alright, So again, we're trying to figure out what A, B, and C are, because once we figure out what those are, then we will have our cubic that passes through all these points. Okay? So we don't really need the points anymore. We have all the information we could possibly extract from them. So I'm just going to write on this side of the board. Okay. The first thing that I see personally is that I can add these two equations together. So when I add them together, what happens, so let's just write down what we're doing. I'm doing 1 plus 2. Okay. And when I do that, what do I get? The reason why I wanted to do that because it kills out the c, right? Because if I add minus c and plus c, it becomes nothing. So when I do the addition, what does it become? It becomes, oh, it also kills out the a's. That's very nice. So really all we get is 2b is equal to 5 plus negative 1 is minus 4. Yeah. And then b, of course, is equal to negative 2. All right. Oh, sorry. 5 minus 1 is 4. Okay, so b is equal to 2. Yeah, I can't add. All right, so that gives you one of them. So now you can put in, wherever you see a b here, you can put in b equals 2, and then solve for the other two. Now, that should not be too difficult. It's 2 equations, 2 unknowns. But, I mean, if this is your first time doing 3 equations, 3 unknowns, it can be a little bit daunting. I can understand that. So this just shows you how to get one of them, and then just apply the same procedure to get the other two. In the end, though, you should get the following. You should get that A equals 1, B equals 2, C equals minus 4, and D equals 3. Okay? Yeah, I think that's all I wanted to say for that. So this is the answer that you should be getting. Sorry. Yeah, I think that's about everything I wanted to say for this. So these are called finite differences. Kind of difficult. The next thing that I'm going to do is a difficult problem regarding long division. Okay? Here's the problem. So, suppose, okay, Triple is giving up today. So suppose we have x squared plus 4x minus 3 as, suppose this thing is a factor of the larger polynomial x to the 4 plus 6x cubed minus 2x squared plus, here's the weird part, mx plus n. What is m and n? Okay? Kind of difficult. So this one's pretty tough. Your first instinct may be to try and use the factor theorem, but looking at this quickly reveals that you can't, because up here what do we have? We have a quadratic factor. And remember, we can only use synthetic division when we have linear factors. So we're going to have to do this the long and hard way, which is through long division. Okay, so let's set up our long division, because at this point, you know, there's no black magic that you can do to simply pull out m and n out of your hat. You have to use the dirtiest tricks, anything that you can think of. Okay, and in this case, long division just happens to be the easiest thing. So, what does it mean for this thing to be a factor of the other thing? It means that if I divided this by the other thing, the remainder is going to be 0. So we should put ourselves a reminder here that the remainder of the division is 0. And we get that from the fact that this is a factor. Okay? So it makes sense to do a division here. And that's exactly what we're going to do. Alright. Let's see. So how many times does x squared go into x to the 4? Hopefully you've had some practice with this from last week, and you can realize quickly that it's x squared. So x squared times x squared gives me x to the 4. So I'll put an x squared up here, and then multiply this x squared out. So this gives me x to the 4, x squared plus 4. Sorry, I think I'm going to switch markers right about now. Okay, x squared plus 4x. Right. So you multiply this out, you get 4x cubed minus 3x squared. Okay. Do your subtraction, you get 0 here, 2x cubed, minus 2 minus minus 3 is x squared. Okay. It's not going to look pretty when we get to the letters, but this is all we can do for now. So how many times does x squared go into 2x cubed? Well, it goes in 2x times. So we'll put up here a 2x. Okay. At this point, even I don't know what I'm doing. I'm still not sure whether this is the right thing to do. However, this is the only thing I can think of doing because of this fact here. Okay. So the important thing in math is that whenever you're given a question, a good question will give you all the information that you need to solve it. Okay? And this is the only information that we have. We don't know what m and n are. So we have to use whatever tools we have. Okay? It's not like we have a choice here in what to do. So on one hand, it may seem that like the choice of doing division is pretty arbitrary, especially with these variables involved. However, the more you think about it, the more you realize that you don't really have any other options. So this is your best shot at getting an answer. Okay? So continuing on, we multiply this out. This gives us 2x cubed plus what? 8x squared. And then this just gives us minus 6x. Drop down the m. Okay? And then perform subtraction. 0. X minus 8x squared is minus 7x squared. M minus minus 6 is m plus 6. Okay, do you see how I tackled that? All I did was pretend that m was a number. Okay? I don't let the fact that it's a letter faze me. Okay? I just do m minus minus 6. It's just m plus 6. Okay? I have no idea still where this is going to lead us, but this is the only thing that we have again. So don't give up now. We're almost at the end. So now how many times does x squared go into minus 7x squared? Well, it goes in negative 7 times. Alright. So then we multiply everything out again. This gives us negative 7x squared. Okay, minus 7 times 4x is going to be minus 28x. And minus 3 times minus 7 is plus 21. Bring down the n, and my goodness, this is looking to be pretty horrible. Okay, what do we have? We get 0. Then we have m plus 6x minus, let me just write it on the side here, m plus 6x minus 28x. It's not a bad thing to write your work on the side when you're feeling overwhelmed with the stuff. Okay, but this is just going to give us, if you look carefully, m plus 34x. Okay. Similarly, over here we get n minus 21. Yeah, so we just get n minus 21. That means that's it, right? So m plus 34x plus n minus 21. All right. So it looks like all of our work has been in vain. All we did was do a division and now we got the letters in the bottom. Except for one thing. Remember that our remainder had to be 0. This is our remainder. We can't divide this anymore. So this is it. This thing is equal to 0. Okay, so how can something times x plus another number be equal to 0? Well, firstly, this thing has to be 0 because if we have any x left, then it's not 0. It's like there's some x. Okay? Similarly here, how can this thing be 0? Well, it just literally has to be 0. So that means we have two equations, two unknowns. In fact, the equations are completely independent of each other, so that doesn't even matter that we have two equations. We just have to solve these, and these are really easy. This gives you m equals negative 34, and n equals 21. And that is, in fact, the answer. So that is how you tackle a question that looks at you in the face and tries to stump you with words and equations with letters in them. Now we're going to consider another problem. This one's going to be a word problem. So, I mean, it may not seem very apparent that there are very good word problem questions that you can ask about polynomials, and that for the most part is true. Polynomials are they're very mathematical objects. It's difficult to connect them to real life scenarios. However, there's one particular example that is going to make good use of everything that we've done so far, and that is the classic volume in a box problem. Okay, so here's how this problem works. Basically, you get a sheet, a flat sheet, okay, and you want to make a box out of it. Now, how do you go ahead and make a box out of this? Unless you know some very clever origami, the most efficient way to do it is to actually make some cuts first. What you would do is you would make a cut, a sort of like rectangular cut here, 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 and here, right? And then what that would leave you with is something that looks like a Swiss cross. So let me just draw it like that. Okay. And something like that. It's not perfect. It's really not perfect. It's embarrassing, actually. But something like that. Okay? And then what you could do is you could fold up along these edges to get your box. Okay? And that would give you your box with no top. Right? So that's kind of the setup of this problem. Now the only question is, given some box with length x and y, what does this imaginary rectangle here, what does that have to be in order for us to get this box, right? And notice that this has to be a square because the heights here and here have to be the same in order for it to match up and glue nicely into a box, right? So let's do a concrete example of this. And we'll see how it connects to polynomials. All right. So, a rectangular piece of paper measures 10 centimeters by 8 centimeters and must contain a volume of 48 centimeters cubed. Okay? So the question is, what size of square must be removed? And of course we're talking about the corners, right? Because remember in our diagram we have to remove the corners. And from the corners we remove squares, right? So we should use our, first our little diagram here. I'm going to draw it flat now. Okay, so here's our sheet, and we're told it's 8 by 10. Okay, and its volume is 48 centimeters cubed. Now volume for a rectangular prism is pretty easy. It's just length times width times height. Okay, and if we cut out rectangles, on these corners, and these rectangles, sorry, these squares, right? They're squares. Keep having to remind myself. But if we cut out squares with side length x, then that means our height is going to be x, right? What is our width going to be? Well, I'll consider this as the width, right? So it's going to be 8 minus, I can just look here, 2x. 8 minus 2x, okay? Let me just make it clear what I'm doing here. So remember in our image, we have this box, and we cut out these corners, and then we fold up everything, right? So this length here is going to be the width. So this is 8 minus 2x. And what is the other one? The one's the length. This is going to be 10 minus 2x. Okay, that's good. This looks like a polynomial. This looks like a polynomial in factored form. All right? But now what's the question asking? The question is asking, what does x have to be in order for this box to contain a volume that is 48 centimeters cubed? So if we multiply all these together, it has to give us 48. Okay? So basically, we are solving for x. We're trying to solve this polynomial equation for x. Okay? So now that we've got the algebraic problem, we've translated our word problem to an algebraic problem, we can remove all the words. So get rid of all these. We don't need them. Instead, we are now going to solve the problem, which should be familiar to you by now if you've been doing the homework correctly, which is how do you find x in this question. So the first thing I want to do is I want to turn it into one of those factored form polynomials, except this 48 is out here, and that's going to be a problem. And no, you cannot just flip the 48 to the other side and have all your problems solved. You're not going to have a factored form after that. It's going to look like x times 8 minus 2x times 10 minus 2x minus 48 equals 0. And that, like, this is not in factored form. So there's no way around it. We have to multiply this thing out. We can make our lives a little bit easier and multiply through by x, but it doesn't really change that much. We eventually have to multiply everything out together. Okay. So I'm going to erase this line of work that we don't want. Okay. So let's expand this thing. All right. I will use my grid method. You can do whatever method you prefer. So this is 80x. This is minus 20x squared minus 16x squared plus 4x cubed. All right, and then so this thing is going to be equal to 4x cubed minus 36x squared plus 80x, and then bring over the 48 minus 48. Okay, now this looks like something that we can do. All right, so let's go ahead and start trying to solve this. All right. So let's see. Let's try some test values. I can immediately see, I think 1 will work. Yeah, I think 1 will work because you get 4 minus 36 plus 80 minus 48. And that to me looks like it adds up to 0. So we are going to try to divide by x minus 1. So our first divisor is x minus 1. Okay? And from here on out, it just becomes your standard problem for synthetic division. So I'm just going to rewrite the thing. It is 4 minus 36, 80 minus 48. And we're dividing by 1. Do your synthetic division. I'll do mine really quickly. Minus 32, minus 32. This becomes 48. This becomes 48 and 0. All right, so this translates to 4x squared minus 32x plus 48. You may notice that you can factor out a 4, so let's go ahead and do that. Okay, and then you can factor this thing. This just becomes 8 minus what? 6 times x minus 2. And then bring in our factor that we took out earlier. And this is a factored form of our polynomial, x minus 6, x minus 2, x minus 1. All right, so that means our solutions are going to be, of course, whenever this thing is equal to 0, which means either of these have to be equal to 0. This gives us the solutions, x equals 1, 2, or 6. All right? Now, you may be thinking, so that means any of these will work, right? Well, let's try. Let's try and see what happens. All right, so remember when we had our little box, I'm going to redraw the diagram here. Okay, something like that. We had here, this length is x, this is 8 minus 2x, this is 10 minus 2x, okay? And we have x, right? So if we try x equals 1, what are the dimensions of our box? And the reason why I'm going through this is because something very strange is going to happen. And I want you to take very good note of this. So if we do it like this, our dimensions are 1 by 8 minus 2 is 6, by 10 minus 2 is 8, which is 48. So we're good. X equals 1 works. What about x equals 2? If we try x equals 2, right, then we get what? 2 times 4 times, what is that? 6, which is also 48. And that's also good. Now let's try x equals 6. Okay, we get 6 times 8 minus 2 times 6 is 12, so 8 minus 12 is minus 4. And then we have 10 minus 2 times 6, which is minus 2. Okay, and this is also equal to 48, except have you ever seen a box whose width is negative 4 centimeters? Yeah, so this is not a valid answer. Therefore, our answers are actually just x equals 1 and x equals 2. Always very important to double check this step, because this is the one that can really get you in the end. Now, this is just one example. It's one of the more difficult examples of these polynomial word questions, but pretty much all of them can be solved the exact same way as we did here. Okay, there's really no difference at the end of the day. So that is all I wanted to talk about for that example. In the remaining time, I'm going to discuss the imaginary roots. Now, these are not graphically very interesting because they don't tell you anything actually. However, there is a very beautiful theory that is connected to these theories of imaginary roots, and that's called complex analysis. So if you recall from the first lecture, the complex plane, C, is just the real numbers, but you add on to it the imaginary component I, which is the square root of 1, right? Now the complex plane looks like this. So remember the real line was just a line? The complex numbers are an entire plane. This is how it works. You get 1, 2, 3, and so on. -1, -2. So these are just your real numbers. This is your real line, R. But here we call this the imaginary axis, I. And on it, we get i's. I, 2i, 3i, -i, -2i, -3i, and so on. Okay? Every point on this plane represents a complex number. This point, for example, represents 2 plus 3i. Okay? Now, the reason why I'm bringing this up is because a lot of our quadratics have imaginary solutions. So for example, if you try to solve the quadratic x squared plus 1 equals 0, you get x equals plus or minus root -1. But root -1 is just I, so your answers are actually plus or minus I. Okay? I would like to introduce some terminology here. So definition, given a complex number of the form a plus bi, its conjugate is just the number that is the exact same but reverses the plus sign on the imaginary component. So its conjugate is a minus bi. Okay? Here's the fact. Okay? Fact. Complex roots of a polynomial come in conjugate pairs. And this may not seem super overwhelming at first. However, once you study enough math and you start to realize how deeply this theory of complex numbers pervades everything, this is actually a very beautiful fact. Because it tells you that there's some nice symmetry to whatever is going on with our roots. Okay? So in other words, suppose, like here's a perfect example of one, right? X squared plus 1, that's a perfectly fine polynomial. And look at its roots. Its roots are plus and minus I. Okay? Plus and minus I, those are conjugate pairs, right? You can think of plus and minus I as the complex number 0 plus I and 0 minus I. So by conjugate pairs, I mean if you have one, then you also have the conjugate pair. You can never sort of get rid of it. Okay? And this is unlike what happens in the real line. In the real line, you could have a polynomial with roots like 1, 2, and 6. There's no symmetry there. But with complex roots, you always get this nice symmetry, this symmetry of conjugate pairs. Right? Let's do another example. And then we'll go back to an example that was troubling us or something similar to what was troubling us in the last lecture, which is when we had a quadratic that we could not reduce properly. All right. So I think I remember. Yeah. All right. Okay. So what I wanted to talk about then was how to factor out these quadratics. So we know the quadratic formula. minus b plus or minus square root of b squared minus 4ac, all that over 2a. And remember, the discriminant tells you whether your quadratic has real or complex solutions, right? If your discriminant b squared minus 4ac is greater than or equal to 0, you're good. But if it is not, if it is less than 0, we said that this was bad. We said it had no solutions. Okay? This here is what we say to appease high schoolers. Because a lot of people can't wrap their head around the fact that even though your quadratic is doing this, it still has a root. Okay? This thing intersects the x-axis, just not where you would expect. Okay? This is a really, really hard fact to get your head around, right? This is the y-axis, the x-axis, and your quadratic here, although it does x-axis, here, it does touch the x-axis in another realm, in the complex realm. Okay? And that's what we saw with the x squared plus 1. Okay? So now I want to go through an example that deals with these complex roots. One typical example that we already did was x squared plus 1, but we'll do a more complicated one. So for example, I can think of, let's try x squared, 2x squared plus x plus 1. Okay? So imagine you had your factored polynomial. You factored your polynomial and it became like, I don't know, something like this. Let's say this was your factored form polynomial. Okay? So you would say the roots, your real roots, are x equals 3 and x equals 3 over 2. Right? But that's not all of the roots. There are also complex roots. Okay? So let's go and figure out what those are. So if we do that, what do we get? Okay. So 2x squared plus x plus 1, we'll use the quadratic formula to find the roots. We do the quadratic formula, we get minus 1 plus or minus square root of 1 squared minus 4 times 2 times 1, all that over 2 times 2. This is the same thing as minus 1. I'm going to just work on the inside. 1 minus 8 is minus 7. And this is just 2 times 2, which is 4. Okay? But the minus 7 is what really? It's just 7. Minus 7 is equal to 7 times minus 1. And we know that if we do roots minus 7, this is the same thing as root 7 times root minus 1. That's just our basic properties of radicals. So if we apply this here, what we really get is the following. Minus 1 plus or minus root 7 I, all that over 4. Because square root of negative 1 is I. Okay? Now, look at this. This is once again our complex conjugate pair. Because we have, on the real side, negative 1 over 4. And on the complex side, we have square root of 7 over 4. And the plus or minus indicates a conjugate pair. That's really why the plus or minus is there. Because when you're taking care of your imaginary roots, you need the complex conjugate, which is the minus side. Okay? Alright, so that's all I wanted to talk about with these complex roots. I just want you to know that they are there and that your teacher may require you to learn these. I have seen tests where these are like literal things that teachers ask for. And there are also examples of schools that do not do anything with complex numbers because it just scares people. However, I wanted to show you in this brief little introduction to complex numbers and these complex roots that imaginary numbers really are quite beautiful, and there's nothing really to be scared about the square root of negative 1. In fact, once you work with it long enough, the symmetry that arises out of complex numbers is really quite beautiful. Okay? I just wanted to end off on one final note about polynomials. And this is a major theorem in what we call abstract algebra. Okay? But it is stated in terms that you will still understand. Okay? This is called the fundamental theorem of algebra. And it goes like this. Given a degree n polynomial with real coefficients, that means your coefficients come from the real numbers, it has exactly, no more, no less, it has exactly n roots in the complex plane. Okay? This is a magnificent fact. However, it tells you that when you're doing these things, right, these problems with the roots and the imaginary roots and all that, you may be missing out on imaginary solutions because you won't find all of your roots in the real numbers. You'll find all of them in the complex plane. And the fact given by the fundamental theorem of algebra is that there are exactly n roots, but only in the complex plane, not in the real plane. Okay? So do not use this when you're doing your work. Just know for a fact that it is true, and that if you want to find all of your roots, you would have to look in the complex numbers in order to get them.